What if the Big Bang wasn't the beginning but a rebirth? What if our entire 93 billion light-year observable universe is just a single object inside a much larger, older cosmos? This isn't science fiction, it's a possibility being explored by theoretical physicists, challenging our most fundamental understanding of existence. The clues might be hidden in plain sight, in the behavior of black holes and the baffling arrangement of the most distant galaxies spotted by the JWST. Let's explore this mind-bending possibility together. The standard Big Bang model. So, how did we arrive at our current picture of the universe? The story most of us know is the standard model of cosmology, first mathematically conceptualized by the Belgian priest and physicist Georges Lemaitre in 1927. It states that our universe exploded into being 13.8 billion years ago from a point of extreme density. From this intensely hot state, space itself began to expand. Over billions of years, gravity sculpted this expanding cosmos, pulling matter together to form the vast, web-like structure of galaxies we observe today. This model is incredibly successful. It explains the faint afterglow of the Big Bang, the cosmic microwave background, and it accounts for the accelerating expansion of the universe. This acceleration, confirmed in 1998, is often attributed to dark energy, which makes up about 68% of the universe. When combined with dark matter, at around 27%, it appears 95% of our cosmos is made of stuff we can't see or understand. This means that all the stars, planets, and galaxies we can observe make up a mere 5% of reality. The bottom line is the standard model, for all its successes, leaves us with the biggest questions in science completely unanswered. The black hole universe theory. What if there's a more elegant explanation, one that doesn't require inventing new particles or mysterious forces? A radical alternative, championed by physicist Nikodem Poplawski, proposes that our universe was born inside a black hole within a much larger parent universe. This idea flips our perspective on cosmic origins entirely. Instead of a singularity appearing from nothing, the theory suggests a physical process, the gravitational collapse of matter in a parent universe. Think of it like a star many times the mass of our sun collapsing to form a black hole, but on a cosmic scale. In this model, what we perceive as the Big Bang was actually the moment our universe formed inside that parent black hole. This framework elegantly resolves the issue of what came before the Big Bang, as the parent universe provides a clear preceding state. This cyclical model redefines our cosmic address, demoting our entire universe from everything that is to just one bubble in a potentially infinite cosmic foam. It also provides a physical source for the energy and matter in our universe, sourcing it directly from a pre-existing parent cosmos. In essence, the matter that makes up you, me, and the stars didn't appear from nothing, but was recycled from a previous cosmic iteration. Quantum mechanics and degeneracy pressure. Here's where things get really interesting, and it hinges on a core principle of quantum mechanics. Have you ever wondered what stops a dead star from collapsing forever? The answer lies in a rule established by the brilliant Austrian physicist Wolfgang Pauli. His exclusion principle states that identical particles, like electrons, cannot occupy the exact same quantum state at the same time. When gravity tries to crush matter into an incredibly small space, this principle creates a powerful outward push known as degeneracy pressure. The more you squeeze, the harder the particles push back. This is the force that supports white dwarfs against collapse, where matter is packed to a density of over 1 million kilograms per cubic centimeter. In even more extreme objects like neutron stars, the pressure is even greater, holding up against densities of over 100 trillion kilograms per cubic centimeter. This pressure is fundamentally different from thermal pressure, which supports a star like our sun, as it doesn't depend on temperature at all. Proponents of the black hole universe theory argue that this same quantum pressure could operate on the scale of an entire collapsing universe, offering a mechanism to avoid the infinite singularity. The bounce mechanism. So, if a universe collapses, what happens when this quantum pressure kicks in? Instead of crushing down to an infinite point, a singularity where physics totally breaks down, the collapse could actually halt and then rebound. This is what's called the Big Bounce, a concept that's been heavily explored in loop quantum cosmology by physicists like Martin Bojewald. In this scenario, as the matter from a parent universe collapses, it gets really close to the maximum density allowed by physics, which is called the Planck density. That's about 5.1 times 10 to the 96 kilograms per cubic meter, which is Honestly, just mind-blowing. At this extreme, quantum gravity effects become so powerful that they basically overwhelm everything else. This force stops the collapse in its tracks and triggers a massive, explosive rebound. The rebound itself would be incredibly brief but unbelievably violent. Essentially, it resets the cosmic clock for a brand new universe. For any observer inside this newly expanding region, the rebound would look and feel exactly like a Big Bang, and it might even preserve information from the previous cosmic cycle. Interestingly, this bounce could also offer a potential solution to the black hole information loss paradox, which is a major conflict between general relativity and quantum mechanics. The paradox is all about what happens to the information about matter that falls into a black hole if the black hole eventually evaporates. A bounce mechanism suggests that this information isn't destroyed, it's actually carried through the rebound event into the new universe, preserving the fundamental laws of physics. Evidence from early galaxies. This might all sound like fascinating speculation, but where's the evidence? Well, it might be hiding in the deepest images of our universe, captured by the James Webb Space Telescope. According to the standard model, galaxies should build up gradually over time. But JWS is finding galaxies that are, honestly, bafflingly massive and mature. For example, the GLASS JWS Early Release Science Program, which includes astronomers like Rohan Naidu, has identified galaxies such as GLASS Z12 at a redshift of 12. That means we're seeing them as they were just 350 million years after the Big Bang. These galaxies are already 1 billion times the mass of our Sun, which is way larger than our models predicted was possible so early on. And to make things even more puzzling, these ancient galaxies seem to host supermassive black holes that are millions of times the Sun's mass, a phenomenon that standard models really struggle to explain so soon after the Big Bang. The Big Bounce model, however, offers a potential explanation. It suggests these black holes could actually be relics that survived from the previous cosmic era, acting as gravitational seeds for the next round of galaxy formation. Galaxy rotation mystery. Now let's talk about another cosmic puzzle that might just point to the same conclusion. In a random and uniform universe, you'd expect galaxies to be spinning in all sorts of directions, with a roughly 50-50 split between clockwise and counterclockwise rotations. But that's actually not what we see. A study from 2020, which analyzed over 200,000 spiral galaxies and was led by computational astronomer Lior Shamir, found a significant imbalance. There seems to be a preferred direction of spin, an alignment that stretches across vast regions of the cosmos. The odds of this asymmetry happening purely by chance are less than 1 in a billion. This unexpected alignment, seen across billions of light-years, suggests that the processes during the universe's formation weren't as random as we once thought. This large-scale pattern actually challenges the long-held assumption that the universe is the same in all directions, which is a principle that underpins pretty much all our cosmological calculations. And this isn't just a small localized effect. The pattern of cosmic spin is coherent across billions of light-years. Shamir's analysis shows that the distribution of spin directions fits what's called a dipolar pattern, meaning it has a distinct north and south pole, kind of like a spinning magnet or a planet. Creating such a large-scale, coherent structure after the Big Bang would be extremely difficult, which points instead to a fundamental property that was imprinted on the universe right at its very creation. Schwarzschild cosmology. So, this idea of a universe inside a black hole isn't entirely new. It actually falls under a concept known as Schwarzschild cosmology. The name comes from Carl Schwarzschild, who, way back in 1916, found the first exact solution to Einstein's field equations. That solution describes the spacetime around a spherical mass, what we now call a black hole. The model suggests that the observable universe is, in fact, the interior of a black hole existing within a larger parent universe. From our perspective, the Big Bang was the formation of this black hole, and, from the outside, our entire cosmos would just look like a regular black hole. The size of this black hole's event horizon is defined by the Schwarzschild radius, and for a universe with the mass of ours, this radius is remarkably close to the radius of our observable universe. Mathematically, the singularity at the beginning of our universe is similar to the singularity at the center of a Schwarzschild black hole. The edge of our observable universe, a sphere with a diameter of 93 billion light-years, acts much like a black hole's event horizon, a boundary from which light cannot escape to an outside observer. Black holes as universe creators. Let's take this idea to its logical conclusion. If our universe was born inside a black hole, what does that imply about the estimated 100 million stellar mass black holes in our own galaxy? It suggests that each and every one could be a gateway, a seed for a new baby universe. This paints a picture of a vast cosmic ecosystem, a multiverse where universes are constantly being born. This concept, known as cosmic natural selection and explored by physicist Lee Smolin, could even offer an explanation for the fine-tuning problem, the mystery of why the fundamental constants of physics are so perfectly set for life. If universes are constantly being created, then perhaps only those whose physical laws allow for the creation of stable black holes can themselves reproduce, leading to a multiverse dominated by life-friendly universes. This theory proposes that our universe is so adept at creating black holes precisely because it was born from one, continuing an unending cosmic lineage. Smolin's theory suggests that the physical constants, like the strength of gravity or the mass of an electron, could slightly mutate with each new universe born from a bounce. Universes with constants that are better at producing black holes will have more offspring, and over countless generations these properties will become dominant. This makes the fine-tuning of our universe for life not a lucky accident but a predictable outcome of cosmic evolution on an unimaginable scale. Torsion and space-time twisting. For a universe to bounce instead of collapsing into a singularity, you need a powerful repulsive force at extreme densities. One candidate for this force comes from an extension of general relativity known as Einstein-Cartan theory. The mathematics behind this were developed in the 1920s by the brilliant French mathematician Élie Cartan. This theory incorporates a property of spacetime called torsion, which accounts for the intrinsic spin of fundamental particles. This spin is a fundamental quantum property like mass or charge that gives particles an inherent angular momentum. In standard general relativity, spacetime can bend, but it cannot twist, making the inclusion of torsion a significant modification needed for this theory to work. According to physicists like Nikodem Poplawski, at the densities found inside a black hole, the interaction between torsion and the spin of particles would create a powerful repulsive force. This torsion-induced bounce would be the mechanism that creates a new universe inside every black hole, making them not just cosmic destroyers but creators. Cosmic anisotropy. The evidence for a preferred direction in galaxy spins points to a concept called cosmic anisotropy, the idea that the universe is not the same in all directions. This directly challenges the cosmological principle, a foundational assumption in modern cosmology. This isn't just about galaxy spins. Anomalies in the cosmic microwave background radiation, first noted in data from the WMAP satellite and later confirmed by the Planck satellite, also suggest a large-scale alignment. Physicist João Magueijo famously dubbed this the axis of evil because it aligned with our solar system's plane, a result so strange it had to be a mistake, except it kept showing up with a statistical probability of being random at less than 0.1%. These anomalies, once dismissed as statistical flukes or errors in measurement, are now forcing a re-evaluation of fundamental assumptions, which is exactly how science progresses. The cosmological principle of isotropy has been a cornerstone of cosmology for nearly a century, so challenging it is met with significant scientific skepticism. However, as observational data from projects like the Sloan Digital Sky Survey and the Planck satellite becomes more precise, these persistent anomalies are becoming harder to ignore. If the universe truly does have a preferred direction, it would force us to rewrite our most basic models, and would strongly imply an origin story that involves rotation, just as the black hole universe theory predicts. From the impossible galaxies seen by JWST to the mysterious alignment of galactic spins, we are faced with observations that don't quite fit our standard story of the cosmos. The idea that our universe is inside a black hole, born from a cosmic bounce, offers a potential framework to explain these anomalies without inventing new physics. It suggests we might be part of an endless cycle of creation. What do you think? Are we living inside a black hole? Let me know your thoughts in the comments below. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Space Facts. So, what if the most terrifying message from the stars wasn't actually a broadcast? but an object. And what if that object wasn't just, passing through, but actually reporting back to something else out there? In 2025, officials confirmed the detection of our solar system's third interstellar visitor, an object they called 3I Atlas. But as they decoded its transmissions and analyzed its totally impossible flight path, they confirmed a fear that humanity has honestly held for centuries. This wasn't just some random rock, it was a messenger. So, let's explore this together. The impossible visitor. So what happens when a visitor from another star system doesn't just tumble through, but actually navigates? When the Vera C. Rubin Observatory in Chile first flagged 3I Atlas in early 2025, it immediately defied every known classification. Unlike our previous interstellar guess, this object showed something that, sent a chill through every Mission Control Center-controlled flight patterns. Dr. Karen Meach, a University of Hawaii astronomer famous for her work on Oumuamua, was among the first to point out that its trajectory was, quote, non-ballistic, to a degree that is simply not natural. It executed deliberate, impossibly precise course corrections. Its sheer scale was staggering. It was surrounded by this massive 700,000-kilometer coma, a glowing envelope of gas and plasma nearly half the diameter of our own sun. But unlike a comet's coma, this one didn't sublimate chaotically. It pulsed, beating like a cosmic heart with powerful electromagnetic signals at a frequency of 1.42 gigahertz. The hydrogen line, which is pretty famous in SETI circles, firing in a perfect rhythm, once every 147 seconds. As this impossible visitor carved its way through our asteroid belt with surgical precision, one chilling question began to emerge. What if this thing wasn't exploring, but was actively reporting back? When physics stopped making sense. Here's where the story honestly takes a sharp turn from scientific curiosity into a genuine threat. Most objects from beyond our solar system follow these chaotic trajectories, their paths just dictated by gravity. But 3I Atlas showed us something entirely different. Its path allowed it to drift past several planets in ways that maximized gravitational efficiency, a maneuver that reminded JPL engineers of those complex gravity assist routes they designed for probes like Voyager. When celestial mechanics experts like Jacques Lasker from the Paris Observatory ran the orbital simulations backward, they found something, statistically impossible without intelligent intervention. The path of 3I Atlas required navigating through dense meteoroid streams and planetary collision zones with a mathematical elegance that was honestly breathtaking. Its trajectory deviated from a purely gravitational path by a measured 0.05 arc-seconds per hour, a tiny but constant thrust that had no visible source. It moved like a grandmaster's chess piece on a cosmic board, avoiding every conceivable threat with a precision that suggested either advanced, long-term planning, or some kind of sophisticated real-time control. This wasn't just a random space rock wandering through the cosmos. It was, as some scientists began to describe it, exhibiting piloted behavior. The object that defied reality. The unsettling feeling that we were dealing with something far beyond our comprehension only got stronger when NASA, under the guidance of senior JWST scientists like Dr. Jane Rigby, pointed the James Webb Space Telescope toward 3I Atlas. The results that came back didn't just challenge our understanding, they totally rewrote the rulebook. The thermal readings showed a consistent, stable temperature of 120 Kelvin, with rhythmic heat emission patterns that pulsed in sync with its radio signals, a behavior that, honestly, just defies thermodynamics. Webb spectrography revealed materials never before seen, including hyper-reflective compounds that returned almost 99% of the light that hit them. But the most disturbing discovery was a faint, recurring electromagnetic anomaly echoing from within. This low-bandwidth frequency at 408 MHz repeated every 147 seconds, matching the exact signature of a known pulsar, PSRB 1919+21. The problem, as any physicist would tell you, was that the object had no spinning core and no magnetic field capable of generating such a signal. It looked like it was mimicking something it had encountered, or even worse, actively communicating with something beyond our detection capabilities. Two visitors, one terrifying pattern. The mystery deepened significantly when researchers cross-referenced the electromagnetic signature of 3I Atlas with archived data from Oumuamua. The comparison revealed something that honestly sent shockwaves through the scientific community. The exact same 147-second frequency had been detected briefly in Oumuamua's data, a faint 3 sigma detection that was initially dismissed as noise. The crucial difference, though, was that 3I Atlas's signal was a powerful, sustained 50 sigma detection, an unmistakable beacon. This discovery, championed by controversial Harvard astronomer Avi Loeb, completely reframed our understanding of both objects. Oumuamua had puzzled scientists, but now a disturbing pattern emerged. The evidence suggested that Oumuamua may have been a reconnaissance probe. If this theory held merit, then 3I Atlas represented something far more significant, not passive observation but active engagement. It was, in effect, the difference between a single radar ping and a fully operational surveillance system. Some researchers now theorize that Oumuamua was the lock, and 3I Atlas is the key, designed not just to observe but to unlock something, whether buried on our planet or awaiting activation in orbit. When space objects make calculated decisions. Just when scientists believed they had mapped 3I Atlas's future trajectory, the object performed a maneuver that, honestly, shattered every remaining assumption. Telescopes in Chile and Hawaii recorded a subtle but unmistakable course shift that couldn't be explained by gravity or solar wind. The object veered slightly off its projected arc, executing a 15-meter-per-second delta V that realigned its vector, bringing it 1/10 of an astronomical unit closer to Earth's orbital plane. To mission analysts at NASA's Deep Space Network at JPL, the implications were, well, alarming. The timing and precision of this maneuver implied conscious decision-making. Even more intriguingly, the maneuver occurred precisely when the James Webb Space Telescope had achieved its optimal tracking position, suggesting the object was not only aware of our surveillance efforts, but was reacting to them. This transformed 3I Atlas from an astronomical curiosity into a potential confirmation of technologies far beyond our own. It was no longer a passive object of study, it was an active participant in a cosmic dialogue we didn't know we were having, a dialogue that was now escalating. Ancient mathematics from the stars. As if its movements weren't enough, independent cryptographers at the SETI Institute, inspired by the lifelong work of pioneers like Dr. Jill Tarter, uncovered something extraordinary. Using Fourier analysis of the pulse's phase modulation, they found precise mathematical ratios hidden within the signal: the golden ratio, Fibonacci sequences, and the first 100 prime numbers encoded in binary. These weren't just arbitrary concepts, they represent fundamental codes that appear throughout the natural universe. The precision of these patterns suggested a level of mathematical sophistication far beyond random cosmic noise. Even more disturbing, though, was the dynamic nature of these signals. The mathematical patterns weren't constant, they changed subtly, reacting to solar activity and even our own radio emissions. Most chilling of all, researchers detected a brief disruption, a single skipped pulse, that matched exactly with the moment James Webb first locked onto it. The object appeared to know it was being observed, and had responded with a mathematical fingerprint that spoke a language older than human civilization itself. Organic chemistry from beyond the stars. So, James Webb's detailed spectroscopic analysis revealed another, disturbing layer to the 3I Atlas mystery. The telescope detected complex carbon molecules on the object's outer shell, specifically polycyclic aromatic hydrocarbons, which are, the building blocks of prebiotic chemistry. These compounds, as astrobiologists like Carl Sagan have long theorized, are the precursors to life itself. But what was really alarming was the purity and organization of these molecules. Unlike the chaotic mixtures found in comets, the compounds on 3I Atlas showed 99.9% isotopic consistency, a level of molecular organization that just doesn't occur naturally in space. The spectral lines at 3.3 micrometers, a key signature of PAHs, were unnaturally sharp and clear. Some researchers, including those at MIT under the guidance of experts like Dr. Sarah Seeger, began to theorize that 3I Atlas might represent a seed ship, an ancient vessel designed not just to explore but to plant the foundations of life on suitable worlds. If this theory held merit, then Earth's location along the object's trajectory might not be a coincidence at all. When Earth responded to the cosmic visitor. When Earth responded to the cosmic visitor, the connection between 3-1 Atlas and Earth became, well, far more unsettling. A classified high-altitude surveillance balloon, managed by the U.S. Antarctic program, detected something extraordinary. The balloon's instruments recorded a powerful microwave burst at 23.5 gigahertz, sharp and centered precisely above the South Pole. Now, at first, this was dismissed as interference, but its timing aligned perfectly with another angular shift in 3Y Atlas's trajectory. Moments after the burst, seismic stations that are part of the global seismographic network recorded ultra-low frequency rumbles across the frozen continent. These deep, resonant frequencies were a perfect 0.0068 Hz, the exact inverse of the 147-second pulses being emitted by 3-1 Atlas. The synchronization was just impossible to dismiss as a coincidence. Somehow, this visitor appeared to be influencing activity on our own planet, possibly triggering responses from systems buried deep beneath the Antarctic ice. The object wasn't just passing by, it was actively interacting with Earth in ways that suggested a technological sophistication far beyond our current understanding. The Asteroid Belt Death Run. 3. I-Atlas is currently navigating through the main asteroid belt, a phase that presents honestly unprecedented risks. Unlike other objects, 3I Atlas cuts directly through the belt's core at a low 5-degree inclination, passing through a region with a particle density 50% higher than the belt's average. The object, moving at a blistering 42 kilometers per second, is surrounded by its massive 700,000-kilometer coma, creating unprecedented interactions with the billions of objects in the belt. Planetary scientists at institutions like the Southwest Research Institute are watching with bated breath. As 3Y Atlas moves through this environment with its powerful electromagnetic signature, it's creating disturbances never before observed. While a direct collision remains statistically low, its gravitational and electromagnetic effects could potentially alter the trajectories of other bodies in unpredictable ways, creating a cascading effect or, more concerningly, redirecting the object itself toward Earth's orbital path. This is a cosmic gamble with planetary consequences. Rewiring our solar system's neural network. Scientists have now discovered that 3Y Atlas's interaction extends far beyond simple gravitational effects. Its complex, dusty plasma envelope is actively interacting with the solar system's magnetic field, creating what researchers are calling an electromagnetic web effect. As 3Y Atlas cuts through the inner solar system, it could be generating packets of charged dust that flow along the sun's natural electric currents toward Earth, potentially triggering geomagnetic storms. But the most disturbing discovery is the most recent. Observations from the Allen Telescope array show that 3Y Atlas has begun emitting a secondary signal, a lower frequency, longer pulse at 700 megahertz, pointed directly toward the Orion constellation. As SETI astronomer Seth Shostak noted, a signal not pointed at us is infinitely more chilling. Some researchers believe it's calling for reinforcements. Others think it's reporting back on its findings. But either way, one conclusion seems undeniable. This was never just an interstellar rock. This was a node, a probe, a messenger, broadcasting to something else that is still on its way. The story of 3I Atlas is far from over. In fact, it may just be the beginning of a much larger, more terrifying story. The mounting evidence, the deliberate course corrections, the mathematical signals, the organic chemistry, and now a broadcast pointed toward deep space, all suggest that this object is not the main event. It is a precursor. It is an announcement that our solar system is no longer a quiet, isolated neighborhood. We may have just accidentally triggered a sequence of events that will fundamentally change humanity's place in the universe, and honestly, we are completely unprepared for what comes next. Thank you for watching Space Facts. What if the most significant discovery in astronomy wasn't just another space rock but something far more extraordinary? Recent observations of 3I Atlas have revealed characteristics so unusual that some scientists are questioning everything we thought we knew about interstellar visitors. This cosmic wanderer's behavior is challenging our understanding of what's natural in the universe. Discovery and initial detection. What are the odds of spotting a cosmic needle in the infinite haystack of space? On July 1, 2025, the Atlas Telescope in Rio Hurtado, Chile, achieved exactly that. detecting a faint moving object initially catalogued as A11PL3Z. This discovery marked a historic moment as astronomers realized they had found the third confirmed interstellar object ever detected by humanity. Following the groundbreaking discoveries of 1I Oumuamua in 2017 and 2I Borisov in 2019, this new visitor was officially designated 3I Atlas, and given the cometary classification C2025N1. However, what makes this detection particularly intriguing is that despite its eventual brightness, 3I Atlas remained hidden from earlier detection due to its challenging viewing angle as it approached from the direction of the Sun. This late discovery, despite the object entering our solar system months earlier, raises questions about how many other interstellar visitors might have passed through undetected. The object's trajectory and timing suggest it may have been deliberately positioned to avoid early detection, a characteristic that has captured the attention of astronomers worldwide. Within days of confirmation, observatories globally began tracking this mysterious visitor, but its behavior would soon challenge conventional explanations for interstellar objects. Extraordinary orbital characteristics. How can an object from interstellar space follow a path so perfectly designed for studying our solar system? 3. I-Atlas possesses orbital characteristics that defy the laws of probability and challenge our understanding of random cosmic motion. The object follows a hyperbolic orbit with an extreme eccentricity of 6.14, making it the most hyperbolic trajectory ever recorded for any confirmed interstellar object. Racing through space at an incoming velocity of 58 kilometers per second, it holds the record as the fastest interstellar visitor humanity has ever detected. What makes these characteristics truly extraordinary is the object's trajectory alignment. Its path lies almost perfectly within the ecliptic plane, with astronomers calculating only a 0.2% probability of such alignment occurring by random chance. This precise positioning allows 3I Atlas optimal viewing angles of all major planets in our solar system, resembling a carefully planned survey route rather than the chaotic trajectory expected from a naturally ejected object. The mathematical precision of this path has prompted some researchers to question whether natural gravitational interactions alone could produce such an unlikely orbital configuration. Unlike typical interstellar objects that enter our solar system from random directions, 3I Atlas appears to follow a route specifically designed for comprehensive planetary observation, raising profound questions about the true nature of this enigmatic visitor from the depths of interstellar space. Suspicious planetary encounters. What are the chances that a random visitor from interstellar space would pass by every major planet in our solar system? The trajectory of 3I Atlas presents astronomical improbabilities that challenge conventional explanations for natural objects. Calculations reveal that this mysterious visitor will pass unusually close to Venus, Mars, and Jupiter, with astronomers determining only a 0.005% probability that such planetary encounters could occur by random chance. Even more suspicious is the timing of its closest approach to the Sun, which occurs precisely when Earth's position blocks optimal observation opportunities, an event with only a 7% probability of random occurrence. This strategic timing ensures that 3I Atlas remains partially hidden during its most vulnerable moment of solar approach, when increased solar heating would reveal the most about its composition and internal structure. The object's path resembles what mission planners would design for a reconnaissance spacecraft conducting a comprehensive survey of our solar system. Each planetary encounter provides optimal positioning for studying gravitational effects, atmospheric compositions, and planetary characteristics that would be valuable to any advanced civilization seeking to understand our cosmic neighborhood. The mathematical precision required to achieve such a trajectory through natural ejection processes appears virtually impossible, leading some researchers to suggest that 3I Atlas might represent something far more sophisticated than a simple interstellar comet drifting randomly through the galaxy. Physical properties and anomalies. How can an object be simultaneously ancient beyond imagination yet surprisingly well preserved? 3I/Atlas presents a fascinating paradox in its physical characteristics that, honestly, challenges our understanding of interstellar object evolution. With an estimated diameter ranging from 1 to 12 kilometers, it's significantly larger than previous interstellar visitors, making it the most substantial confirmed object from beyond our solar system. Age estimates suggest this cosmic wanderer is over 7 billion years old, predating the formation of our entire solar system by billions of years. Despite its ancient origins, 3I/Atlas has earned the distinction of being the brightest interstellar object ever observed, reaching magnitudes that allow detailed study with ground-based telescopes. The object exhibits a 29-hour rotation period with remarkably minimal brightness variations, suggesting an unusually spherical or elongated shape that maintains a consistent cross-sectional area as it spins. What puzzles astronomers most is how an object of such extreme age could maintain its structural integrity during billions of years of interstellar travel, surviving impacts from cosmic dust, radiation bombardment, and gravitational perturbations from passing stars. The preservation of such an ancient artifact raises questions about its composition and internal structure. Most naturally formed objects of this age should show significant weathering and fragmentation, yet 3I/Atlas appears remarkably intact, leading some researchers to speculate about unusual material properties or construction methods that could explain its extraordinary longevity. Comet-like features versus anomalous behavior. Why does 3I/Atlas simultaneously behave like a typical comet while displaying characteristics that contradict cometary physics? This interstellar visitor presents a confusing mixture of expected and anomalous behaviors that have astronomers scratching their heads. On one hand, the object displays clear cometary features, including a faint coma and a short 3-arc-second tail, indicating active outgassing as solar radiation heats its surface. Spectroscopic observations confirm the presence of water vapor and dust particles being ejected from the nucleus, creating the familiar fuzzy appearance associated with comets approaching the Sun. However, several characteristics deviate significantly from typical cometary behavior and challenge conventional understanding. Unlike normal comets that develop extensive flowing tails as they approach the Sun, 3I/Atlas maintains a remarkably compact and dense appearance despite its proximity to our star. The expected dramatic tail development that should occur during solar approach appears mysteriously absent or significantly suppressed. Additionally, the object's outgassing patterns don't follow the predictable models used for solar system comets, with activity beginning much earlier and following unusual intensity patterns. The combination of recognizable cometary features with anomalous behavior patterns creates a scientific puzzle that defies easy categorization. Some researchers suggest these contradictions could indicate an artificial origin designed to mimic natural cometary activity, while maintaining structural advantages that prevent the typical fragmentation seen in natural comets during close solar encounters. Scientific debate: natural versus artificial. Could humanity be witnessing the first confirmed artificial object from another civilization? This question has sparked intense debate within the astronomical community, with Professor Avi Loeb from Harvard University leading controversial discussions about 3I/Atlas's potential artificial origins. Loeb points to the statistically improbable trajectory, precise planetary encounter timing, and anomalous physical characteristics as evidence that this object might represent advanced technology rather than natural formation. His arguments center on the mathematical impossibility of achieving such a perfectly designed reconnaissance trajectory through random gravitational ejection from a distant star system. The object's strategic positioning for optimal planetary observation while minimizing detection opportunities suggests intentional design rather than cosmic coincidence. However, the majority of the scientific community strongly opposes these interpretations, dismissing such claims as irresponsible speculation that, honestly, undermines serious astronomical research. Leading planetary scientists argue that unusual characteristics can be explained through natural processes we don't yet fully understand, pointing to the complex dynamics of planetary system formation and ejection mechanisms. They emphasize that extraordinary claims require extraordinary evidence, and current observations, while puzzling, don't provide sufficient proof of artificial construction. The debate highlights fundamental questions about how we interpret anomalous data and the criteria required to consider non-natural explanations. This scientific controversy demonstrates the challenges of studying truly unprecedented phenomena that push the boundaries of our current understanding. Spectral analysis mysteries. So, what happens when the chemical fingerprints of an object contradict everything we know about cosmic ice? Well, spectroscopic analysis of 3I Atlas has revealed some pretty puzzling discrepancies that honestly challenge our understanding of interstellar object composition. While initial observations detected the expected water ice spectrum, a more detailed analysis actually reveals significant anomalies in the spectral patterns. The observed signals rise precisely where theoretical water models predict they should drop, and this creates a scientific puzzle that's got researchers questioning their fundamental assumptions about cometary composition. This unusual spectral behavior suggests either unknown ice structures formed under extreme interstellar conditions, or maybe even the presence of exotic materials not found in typical solar system objects. The object's distinctive reddish coloration adds yet another layer of mystery, resembling asteroids from the outer asteroid belt, rather than the neutral or blue colors we usually see in pristine comets. Standard models just can't adequately explain this color combination along with the observed outgassing patterns, which suggests some pretty complex surface chemistry, likely altered by billions of years of cosmic radiation exposure. And to complicate matters even further, the active coma surrounding the nucleus interferes with spectroscopic measurements, making it tough to distinguish between emissions from the solid surface and gases in the surrounding cloud. Advanced computer modeling, which tries to separate these contributions, has so far yielded inconsistent results, with some analyses even suggesting the presence of materials that really shouldn't exist in natural cometary bodies. These spectral mysteries have prompted some researchers to consider whether 3I Atlas might contain artificial materials or, maybe even represent a type of object completely unknown to current astronomical science. Dark forest hypothesis implications. Could 3I Atlas represent evidence of a cautious alien civilization following the theoretical dark forest hypothesis? This controversial idea suggests that advanced civilizations, remain hidden to avoid detection by potentially hostile neighbors, conducting reconnaissance missions while minimizing their own exposure. The behavior of 3I Atlas, honestly, eerily matches this theoretical framework, displaying what appears to be deliberate stealth-like characteristics designed to avoid detection during its most vulnerable moments. The object's trajectory ensures it remains partially hidden behind the sun during its closest approach, when increased solar heating would reveal the most information about its internal structure and composition. This strategic positioning allows comprehensive study of our solar system while minimizing opportunities for detailed observation by Earth-based telescopes. The timing and trajectory appear designed for maximum information gathering with minimum exposure risk, resembling the cautious exploration strategy that an advanced civilization might employ when investigating a potentially inhabited star system. The dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin, suggests that civilizations remain silent because revealing their location invites destruction by more powerful neighbors. If 3I Atlas represents such a reconnaissance mission, its behavior demonstrates remarkable sophistication in balancing scientific objectives with survival instincts. The possibility that we're witnessing humanity's first encounter with alien technology conducting a stealth survey of our solar system raises profound questions about cosmic civilization protocols and our place in a potentially crowded but silent galaxy filled with hidden watchers. Historical context and lessons. The discovery of 3I Atlas carries profound implications shaped by our previous experiences with interstellar objects and, the scientific opportunities we failed to fully capitalize on. The first interstellar visitor, 1I Oumuamua, caught astronomers completely off guard when Robert Warwick detected it using the Pan-STARRS 1 telescope in 2017. The object's unexpected rapid exit from our solar system left the scientific community with more mysteries than answers, particularly regarding its strange acceleration behavior that just defied conventional explanations. This missed opportunity, honestly, highlighted critical gaps in our rapid response capabilities for studying rare cosmic phenomena. The second interstellar object, 2I Borisov, discovered by amateur astronomer Gennady Borisov at his Crimean Observatory in 2019, provided a redemption opportunity that was better utilized but still constrained by available technology and coordination limitations. Mark Norris from the University of Central Lancashire emphasizes that 3I Atlas represents our most comprehensive opportunity to date for properly investigating an interstellar visitor using advanced instrumentation and coordinated global observation strategies. The improved detection capabilities of contemporary sky survey systems, combined with enhanced international communication protocols, have enabled unprecedented real-time coordination among research facilities worldwide. Michelle Bannister notes that these lessons learned from earlier interstellar encounters have truly revolutionized our approach to studying these remarkable cosmic messengers. Future observations and implications. What will the next few months reveal about the true nature of this enigmatic visitor? 3. I-Atlas will reach perihelion on October 30, 2025, providing the most critical observation window in its entire passage through our solar system. Following this closest solar approach, the object will re-emerge from behind the Sun in December 2025, offering a final opportunity for comprehensive analysis before it begins its permanent departure from our cosmic neighborhood. Multiple telescopes worldwide are coordinating the most ambitious interstellar object observation campaign in astronomical history, including space-based platforms like the James Webb Space Telescope and Hubble Space Telescope. These coordinated observations aim to resolve fundamental questions about the object's composition, internal structure, and true nature before it becomes too distant for detailed study. The data collected during this critical period could revolutionize our understanding of interstellar objects and their implications for planetary defense strategies. If 3 I-Atlas proves to be artificial, the discovery would represent the most significant moment in human history, confirming that we are not alone in the universe and that other civilizations are actively studying our solar system. Alternatively, if proven natural, the object would still provide unprecedented insights into planetary formation processes in distant star systems and the evolution of materials during billions of years of interstellar travel. Either outcome promises to transform astronomy and our fundamental understanding of our place in the cosmos, making the coming months among the most important in the history of space science. As 3 I-Atlas approaches its moment of truth during perihelion, it carries with it the potential to answer humanity's most profound question: are we alone? Whether this mysterious visitor proves to be an ancient comet or something far more extraordinary, it represents a pivotal moment in our understanding of the cosmos. For more groundbreaking space discoveries that challenge everything we thought we knew, subscribe to Space Facts, where the universe reveals its most stunning mysteries. What if NASA captured evidence of alien technology, and then the live feed mysteriously cut out at the exact same second? In the summer of 2025, while tracking a visitor from another star system, that's exactly what some people believe happened. A single, baffling frame of data was broadcast before a total blackout, showing something that looked unnervingly artificial. Was it a glitch, or a glimpse of something engineered? Let's explore this together. The initial discovery. So how do you find a messenger from between the stars? You build a robotic network to scan the entire night sky. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, did just that. Its networked telescopes in Hawaii, Chile, and South Africa are designed to scan each patch of the visible sky 4 times a night, creating a motion-detecting system for the inner solar system. That evening, its automated software flagged a faint, fast-moving object. Larry Deneau, a principal investigator for the ATLAS project at the University of Hawaii, noted that its trajectory was immediately flagged as hyperbolic. Here's what that means. All objects in our solar system follow elliptical paths forever bound by the sun's gravity. A hyperbolic path is an open curve, proof that the object was moving too fast to be captured and was just passing through. This was only the 3rd confirmed interstellar object ever detected, and it was quickly designated 3 I-Atlas by the Minor Planet Center. Initial follow-up observations using the James Webb Space Telescope revealed it was a cosmic outlier, unusually rich in carbon dioxide. This wasn't just another icy rock, it was a rare visitor from the deep, carrying the chemical signature of a star system far from our own, and its early detection gave humanity a front-row seat. The anomalous frame. Here's where a routine observation turns into a full-blown enigma. On August 18, 2025, just past 0317 UTC, NASA's public live feed tracking 3 I-Atlas went dead. But fractions of a second before the blackout, at precisely 031712 UTC, a final frame was captured and broadcast. At first glance, it's a standard cometary image, a dim, star-like nucleus shrouded in a fuzzy, glowing coma of gas and dust. But in the lower left quadrant, something catches the light in a way that seems impossible. It's a razor-straight glint slicing across the darkness. Not a gentle curve, not an arc, a defined geometric edge with clear start and end points. Independent astronomers running open-source edge detection algorithms flagged the anomaly within hours. Dr. Laura Creedberg, director of the Atmospheric Physics of Exoplanets Department at the Max Planck Institute for Astronomy, was among the first to post a detailed analysis. Her software highlighted a nearly perfect straight line, measuring about 37 pixels from end to end. She noted it reflected sunlight with a sharp, specular quality, meaning it bounced off like a mirror, not scattered like a dusty snowball. This is fundamentally different from how fractured ice or rock behaves. It was completely at odds with the soft, natural contours of the comet, creating a firestorm of online debate. Data verification. In the age of digital manipulation, the first question you have to ask is, was the image real? This is where the story gets even more compelling. The raw data from the NASA feed wasn't just in one place. Within minutes of the blackout, independent citizen archivists had uploaded their own continuous packet captures. Each file, labeled with the same 031712 UTC timestamp, carried a unique SHA-256 cryptographic hash, an unbreakable digital fingerprint. If even a single bit of data were changed, the hash would be completely different. When compared, every single copy matched. Marcus Cole, a retired network engineer in Ohio who runs one such archive, published his checksums on a public repository, stating, "The data is pristine. From NASA's relay to my server, not a single bit was altered. What we have is what the probe sent." This decentralized network of archivists, from universities in Germany to science enthusiasts in Australia, ensures that what the public sees is what the telescope saw. Every copy of the feed showed the exact same anomalous frame, followed by the exact same blackout. The chain of custody, corroborated by third-party time authorities like NIST, was forensically airtight. The evidence is real, the archive is clean, and the mystery remains untouched. Technical explanations. So if the image is real, what about the blackout? Was it a deliberate cover-up? The official line points to something far more mundane: network instability. NASA's live feeds rely on the Tracking and Data Relay Satellite System, or TDRS, which is basically a constellation of satellites that act like switchboard operators in the sky, bouncing signals from deep space to ground stations. Dropouts are not rare. A lead engineer for NASA's Deep Space Network might explain in a technical brief that when a relay satellite moves out of the line of sight of a ground station or passes through a known orbital zone of exclusion, a handover to the next satellite has to happen. Sometimes this results in a handover blank, that classic 2-second gray screen. The DSN logs every single dropout with a specific reason code, and according to those public logs, this event was just one of those routine handovers. But for skeptics, the timing of this particular routine glitch, right down to the exact second the anomaly appeared, is a coincidence that feels just way too perfect to ignore. While dropouts are common, one happening at the precise millisecond an anomaly is flagged by monitoring software is, honestly, a statistical longshot that keeps the debate alive. Digital forensics. Let's zoom in, pixel by pixel. When digital forensics teams analyzed that final frame, they found clues that both deepened and potentially debunked the mystery. The first thing they noticed was that the sharp edge ran perfectly parallel to the borders of several 8x8 pixel blocks. Dr. Hani Farid, a professor at the University of California, Berkeley, and an expert in digital forensics and image analysis, might call this a potential fingerprint of the video codec. To save bandwidth, NASA's feeds use heavy MPEG-style compression, slicing each frame into a grid of macro blocks. When a sudden faint streak appears, the algorithm can exaggerate it, snapping it into a rigid, blocky outline. But, compression isn't the only culprit here. Space is filled with cosmic rays that can slam into a camera sensor and leave a white-hot streak. Analysts flagged a transient line lasting just that single frame as textbook cosmic ray behavior. Dr. Farid and others might propose a double-hit theory. A real, fleeting cosmic ray artifact was amplified by the compression codec, creating the illusion of an artificial edge. However, others could point out the glint had a consistent brightness along its length, which is less typical for a cosmic ray that often has a brighter entry point and a fading trail. 3i Atlas background. To understand the anomaly, you have to understand the object itself. 3. I-Atlas is only the third confirmed interstellar object. Its name comes from the survey that caught it on July 1, 2025. This early detection gave astronomers a rare chance to watch it wake up. The details immediately set it apart. Spectroscopic studies from a James Webb Space Telescope program led by principal investigator Dr. Martin Cordner of NASA's Goddard Space Flight Center revealed a carbon dioxide to water ratio of about 8:1. This is incredibly significant because it suggests the object formed in an extremely cold region of its home protoplanetary disk, far from its parent star, where carbon dioxide ice could dominate over water ice. In our solar system, comets are much richer in water. This means its activity, the jets of gas forming its coma, is driven by this sublimating carbon dioxide, not water ice. The coma itself is a dense dust cloud hiding the nucleus, which is estimated to be under a kilometer in diameter. It's a true alien, born in a planetary system with a chemistry different from our own, sent on a billion-year journey through the dark, carrying clues to its exotic origins. Scientific scrutiny. Every claim about something artificial in space faces a steep climb. The process begins with observation, but to move up the ladder of evidence, the anomaly must survive a gauntlet of scrutiny. Independent teams must see it in their own data, using different instruments. If one observatory reports a geometric edge in visible light, others need to confirm it across different wavelengths like infrared or radio. Dr. Karen Meach, an astronomer at the University of Hawaii's Institute for Astronomy and a leading expert on interstellar objects, might summarize the mainstream view in an op-ed. A single frame from a single instrument, however intriguing, is not data, it's an anecdote. Science requires independent, multimodal verification before we leap to conclusions. Science history is full of exciting signals that vanished under closer inspection, like the BICEP-2 gravitational wave signal in 2014, which turned out to be galactic dust. Until the glint from 3Y-Atlas can be confirmed by other observatories with different equipment, most researchers will hold back. That's how something goes from an oddity to a candidate, and from a candidate to a world-changing discovery. The burden of proof is, and should be, extremely high. 3 theories. So what are we looking at? The debate splits into 3 main paths. The first is pure physics, a theory detailed by a planetary scientist like Dr. Carrie Lease of the Johns Hopkins Applied Physics Laboratory. Comets are violent places. As sunlight heats the surface, jets of carbon dioxide can erupt from beneath the crust like geysers, causing massive thermal stress that can fracture the nucleus, splitting off large shards of rock and ice. His model might suggest the glint is simply sunlight hitting the fresh, perfectly flat face of a newly fractured piece of the comet, a phenomenon known as cleavage in minerals. The second path points to a perfect storm of digital noise, a 1 in a billion collision of a random cosmic ray hitting the sensor at a shallow angle, which is then amplified and squared off by the blocky math of video compression. Many favor this, arguing an illusion is always more likely than an alien artifact, but a third idea keeps resurfacing. Some, like a fringe group of material scientists, propose the edge is exactly what it looks like, something manufactured. The specular reflection is more consistent with a polished alloy or ceramic than fractured ice. It remains the least likely but most elegant explanation for the visual data alone. Broader implications. An event like this ripples far beyond astronomy forums. When a NASA feed cuts at the exact instant an anomaly appears, it sends a jolt through public imagination and scientific policy. Dr. James Evans, a sociologist at the University of Chicago who directs the Knowledge Lab, might write that the event forces a confrontation with a profound possibility in a tangible way that SETI's radio silence has not. It moves the search for extraterrestrial intelligence from a passive listening exercise to an active forensic one. Funding priorities can shift. Lawmakers might propose a Data Transparency in Astronomy Act, mandating real-time decentralized public mirrors for all major observatories. For everyone watching at home, it becomes a test of media literacy. Is this a glitch, a cover-up, or a genuine hint of something bigger? If one frame can change how we search the skies, what happens when the next visitor breaks all the rules? It pushes the line between healthy skepticism and profound wonder just a little bit further, impacting public trust in scientific institutions. The search continues. As of today, the glint in that final frame from 3I-Atlas remains an officially unexplained phenomenon. There is no conclusive evidence to support either a natural or an engineered origin. The technical explanation is plausible, but the timing keeps the question alive. What is clear is that every new visitor from beyond our solar system pushes our technology and our protocols forward. Dr. Paul A. Abel of the NASA Johnson Space Center, who has worked on concepts for rapid response missions, might say the mystery has already fueled calls for automated systems. These systems would use AI to analyze survey data in real time and upon detecting an anomaly like unusual light curves or trajectories, could automatically trigger follow-up observations from other telescopes around the world within minutes. This is a direct lesson from being caught off guard by 3I Atlas. The search for answers continues, not just in old data archives, but in the sky itself, as we wait for the next messenger from the void to make its presence known. The story of 3I Atlas is a perfect storm of data, doubt, and tantalizing possibility. A verified, untampered frame shows something that defies easy explanation, followed by a blackout at the most suspicious moment imaginable. Is it a ghost in the machine, a cosmic coincidence, or the first faint signature of technology from another star? The debate rages on, fueled by that single silent image. Whatever the answer, it reminds us that we are still just beginning to explore the vast, unknown ocean of space. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the cosmos. Thank you for watching Space Facts.